Okay, so yesterday we were working on 13, and we decided that, oh, that's not the right button, this is. We ended up with 183 rounds that were between 3.4 and 6.6. We just went on the spreadsheet and we counted up all of the 4s and 5s and 6s. And it turns out that 183 divided by, how many were there total? 286. We got 64%. How many did we expect? What percentage did we expect? 68%. So seemed to work pretty well, right? All right. So the next question is, how many of the class counts should we consider unusual? How are we going to define unusual? We're just going to pick 2 standard deviations to make it easy. Okay. So we're going to do 5 plus or minus what? 2 copies of the standard deviation 1.6. So 5 plus 2 times 1.6 and 5 minus 2 times 1.6. So basically we're going to count up all of the zeros, ones, nines, and tens. So if I go to my spreadsheet, which is right here. Okay, we got to count up all of the zeros and ones. How many are there? None. Okay, then I go all the way to the bottom and I count up all of my nines and tens. And we have 5 nines, and a 10, so 5. 6, sorry, 5 nines and 1 10. So how many are unusual? 6. Uh-oh, you're on your phone. Were they good looking? No? Well, that's not worth your citizenship deduction. So 6 of them were unusual. How many would we expect? What percentage would we expect to be unusual? So if we draw our normal curve and I cut off everything from -2 to +2, how much is in the middle? It's about 95%. So how much should be in the wings? About 5%. So we take our 6 and divide by 286. So 6 divided by 286, and I got 2%. I expected 5, I got 2. That's pretty close. Okay. Samples are never perfect, but that one's not too far off. Okay. So I'm gonna change. I want this. Okay. So number 15. This is how statistics are done. Setting up a null hypothesis, running an experiment, and then testing the null hypothesis. So we want to know if the coin is fair. Now, everybody flipped a different coin, which is not really the way that we should do it. If we want to know if a particular coin is fair, we should probably flip that same coin over and over and over, but we're lazy. So we're going to assume that everybody had an identical coin. What is the null hypothesis going to say? So the null hypothesis is H naught, well, not equals, H naught says that the true parameter pi is what? What should happen if the coin is fair? 0.5. Right? Okay. And the alternative hypothesis, H sub A, says that pi is, it's either going to be greater than or less than. Which one am I going to use? Greater than. How come? What was our sample percentage? It was higher, right? Now, this is a percentage. You could also say that the parameter is 5 because we're playing a 10-round game. And that's actually going to make a little bit more sense to you today. Technically, we should do pi is equal to 0.5, but we're not going to worry about that today. So because we're doing a 10-round game and we've been working in how many heads there are in 10 rounds, we're going to say pi is 5. What was our average? 5.13, right? So the alternative hypothesis is going to say pi is greater than 5. Now, was our pi value greater than, was our sample value, our x bar, greater than 5? It was. So should I already circle h sub a and reject the null hypothesis? No. I only accept or reject the null hypothesis based off of the p-value. Okay? If p-value is less than 5, then I reject the null and accept the alternative. If the p-value is if the p-value is greater than 5%, then I'm going to accept the null. I shouldn't have done 5s. Oh well. Hopefully this will make sense. Okay, so this is saying 5 heads, right? Okay, so how many of the class rounds had a single head that should say or fewer? Okay, so we are testing. Oh my heavens, I'm sorry guys. We're not testing our. So what happens when you teach with a new book? So pi is less than 5 because I am testing a single head. Okay, so if you flip a coin 10 times and you end up with 1 head, is that coin broken, yes or no? That's the question we're asking. Okay, so we expect 5 heads. The unusual would be less than 5 heads. So how many of the class rounds had a single head? If I went back to the chart that we just looked at, how many zeros or ones were there?
0.
None. Good job, Garrett. Right? There were none. Okay? And how many rounds did we play? 286. So what was my sample percentage? So my p-value was 0%. Okay? Do we think that the coin is broken? Yes, we do. Are we sure? No, we're never sure about anything. But my p-value is less than 0, which means reject h naught and accept HA, which means we throw out the coin, essentially. Does that make sense? That's how a hypothesis test works. Okay? We set up a null hypothesis using what we think should happen. We compare it to what did happen, and then we calculate the p-value by looking at the histogram and counting how many times did something like this occur, and then we divide that by the total number of rounds, and we get a percentage called the p-value that we compare to 5%. In this case, the p-value was smaller than 5, so we reject the null, we think the coin is broken, and we throw it away. Okay? All right. Suppose you flipped a coin 10 times and you ended up with 7 heads. What is my H naught in this case? Pi is equal to 5. That's how many heads we should get. Okay. What is my alternative hypothesis? Pi is greater than 5. Why is it greater than 5 this time? Because our sample had 7 in it, and 7 is bigger than 5. Okay? So how many of the class rounds had 7 or more? Let's go figure that out. So let's keep track of this. 110, 5 nines. Actually, we could just calculate it. So from 287 all the way up to 231. So how many is that? 287 minus 231, 56. So we had 56 rounds that had a 7, an 8, a 9, or a 10. Right? And how many rounds did we play? 286. So 56 divided by 286 means 19.5%. So if I were to draw our normal curve and put 5 in the middle, 6, 7, 8, 9, 10, and I draw a line at 7, this area over here, the number of 7s, 8s, 9, and 10, represents about 20% of all possible outcomes. So my p-value is 20%. What does that mean? We accept the null, which basically means we think the coin is fair. Now, do we actually say the coin is fair? No. We do this really pretentious statistical language where we say we failed to reject the null. There is not enough evidence to suggest that the coin is unfair. They can't just say keep the coin, because statisticians are weird. They say there is not enough evidence to suggest that the coin is unfair. Okay? Make sense? But basically that means keep the coin, don't throw it away. All right, that one is